relationship between the elements in a way that we can sort of see or visualize as a characteristic. Truth be told, here's one of the things that I like to say, and this is something that I learned the hard way because I've never really seen it. If you can't plot it and at least get a good idea how the things are related to one another, how do you expect a machine to be able to do it? If you can't make it make sense to you as a human, you can't use your high-level intellect in order to create a correlation between the items, and then you want the model to go in and find things that you can't see, how can you direct it to what it needs to go to? It needs to be at least somewhat intelligible as a structured set of data. You need to be able to plot something that looks like it's moving in a direction or that it's fixed along a surface or something along those lines in order for it to be able to be characterizable. And you will be able to do that in a variety of ways, right? So you'll essentially be able to say factor 1 versus factor 2 to y, factor 3 versus factor 5 to y. The characteristic then would be the system will take all those things together, and hopefully that the whole becomes greater than the sum of its parts. So even though we're only able to provide a somewhat understanding at each of those factorizations, the combinations of all those factorizations should come together in a way that we can't solve. But if it doesn't make sense to you, if it's just a wild scatter of points, don't expect the model to kind of like be revolutionary and fix everything. It's just not going to do it. Okay, so let's go back for a second to this equation. We looked at the bias-variance trade-off visually and structurally. So let me go ahead and open up my supplemental slides. But you guys should be able to see the supplement slides now. I don't know if they were posted previously. I thought they were, but...
Yes, we have.
Okay.
I have this one.
Okay, good. So supplemental slides sort of gave us an option for understanding the relationship between some of the key elements here visually in a different way than the plots on the PowerPoint, or excuse me, on the PowerPoint plots give us a better interpretation than the ones on the PDF that's from the text authors. Talk about it in just a second again, but to review this topic, and I find this topic to be very important. That's the reason why I'm going back to it again, just for refresher for everybody to get us thinking about how this works. Total error implies that the correlational capability of the model, its ability to take inputs and generate a relational paradigm with some degree of flexibility for the data input across both of our data sets, right? Our first data set is the core set, that is the underlying true distribution, right? So the underlying true distribution could be drawn up as this curvature. This would be or can be prescribed as generative of f of x, right? So the value y is relative to the underlying generative function f of x. So this is what we would say as the true probability density function, right? The likelihood of a sample to fall within or a value to fall within a sample range. When we resample it, right, we're going to start off with the mean, right? And then we'll have a series of individual samples in here, each one sort of polled randomly. And we're going to construct a new distribution. Now note something about this. The mean of this new distribution is not necessarily the mean of the original distribution. We'll call this distribution training. Okay? We've allocated something like 70% of the data to this space. Now, the small delta between these groups is a consequence of this. The tag. Its mean also does not have to be identical, nor its standard deviation, right, relative to the offset of the system. This is statistics, all right? We're just thinking about statistics. We'll talk. I'll throw some stuff in here additionally about this later on, but I want to think about what we're looking at. Why does the performance of testing vary from the performance of training? Despite the fact that they are sourced from the same core f of x, when I attempt to model them, I'm blindly creating f hat, my guess function. So I blindly create f hat from training. So I attempt to model the understanding of the system based upon mean standard deviation and sampling baselines of that environment. But ultimate goal is to make f hat equal to, or approximately equal to, f of x, right? It only converges to f of x when you think about it from the perspective of training and testing being reflective of the original f of x. The composite of both of those together is the closest representation we have of the true underlying distribution. Since we've separated them, we have very similar sourcing, so they come from the same originating space, but they are not the same exact data set. So anecdotal examples can occur, which will do what? They shift the mean, because the random sampling process of the core system, and what's the other consideration? The more samples we have, the more it tends to converge toward the mean, right? The increase, we keep sampling, right? Central limit, law of large numbers, the distribution characteristics will keep increasing the density towards the center of the distribution until we have a normal distribution. So guess what? We have fewer samples here and even fewer samples here. So we're getting further and further away from the true underlying characteristics of the distribution into small deviation shifts, pushes in one direction or another, based upon the randomness of just certain samples having different characteristics. Whenever I say that generalization, I'm talking about the notion of being able to make rules using training and then apply them to testing for the purposes of abstraction in the effect that testing simulates continuing to sample the real world, the natural continuous world, from the underlying root distribution. But when I say that there is a trade-off between the capacity to perfectly match, this is the square bias, this is the capacity to create a perfect match to this underlying distribution in training. But variance is the capacity to create a qualitatively, I guess not qualitatively, a match that has the qualities with parity, right? So training and testing will have parity. They will have roughly equivalent performance with respect to the model. The idea becomes that as f hat of x approaches equivalency in training and testing performance, it will also approach f of x. Everybody understand what I mean by that?
Can you explain it with the f of hat again? I didn't.
Okay, so f hat, this is my guess function.
Yeah.
I can't know whether or not f hat is equal to f of x because I haven't actually collected all the samples yet.
No.
So this is what we call ground truth. Ground truth is technically unknowable because of the fact that we can't have perfect understanding of the system. So all we're going to be able to do is get closer to the objective. So when we think about this from like an AI generative function generative assessment space, what we would say is it is an objective, but it's a blind objective. We're driving in a direction, but we don't know when we've actually arrived. Yes?
So when you said ground truth is unknowable, I'm thinking of an example here, like let's say a denoising algorithm on a photo.
Okay.
If we were training for that, well,
sure.
The ground truth would be like a non-noisy photo.
Correct. Perfect.
So
actually, ground truth is the thing you're taking a picture of.
Oh, okay.
Okay, that's ground truth. That's a really good example. Ground truth is what I'm actually taking a picture of. How close is the picture ever going to get to the thing I'm taking a picture of? How many pictures do I have to take in order to average them, in order to get a perfect approximation of exactly what I'm taking a picture of. All of them. I have to take every picture. Like I have to take 10, 11 billion frames, okay? The reason why is because there will always be some noise in each of the samples, and while the elements of the noise will only correlate with itself, we'll only be able to perfectly extract signal from noise, right? Be able to extract what is signal, f of x, right? What is our model? That is the picture we took, right? So f of x is the actual thing I'm taking a picture of. I'm taking it with a camera that's f hat of x, and I say that what's left over, the elements that I can't eliminate, irreducible characteristics, irreducible noising characteristics. So when I say that I would need a theoretically infinite number of samples, if I had a theoretically infinite number of samples, I would be able to eliminate the irreducible noise. But because of the fact that I don't have that infinite number of samples to be able to integrate out that noising characteristic, I'm always going to be adding a little bit of that. I like to say it's baked into the cake, okay? This is, you make a cake, you put milk and flour and, eggs out there, right? And when I crack the egg into the cake and I mix it up and I bake it and I hand it to you and I go, get the egg back out, right? Which portion's the egg? It's baked in. Okay, when I say error, and this irreducible error characteristic is baked into the system, I mean that it is sort of evenly spread in every single sample. Since every single sample has some noise in it, how do I tell which elements of the system are signal, which are noise? I can only do so by being able to understand this, the true ground environment, what I was actually taking a picture of. What is our ability to measure that ground truth? It's variable in the same way that everything that we do is variable. Everything is an approximation at our best guess at what the actual true characteristics underlying is. That's why I say that thing about, how tall are you? With and without your hair, for those of us who have hair. Those also from the perspective of, it's just these two guys, sorry.
It's all right.
But we have this idea of saying, what tools and devices are we using in order to kind of dancing on the bottom of his face. We have this desire to map that, to model that in a way that provides the capacity, right? If we had this, how well could I map any new sample? Perfectly. It would be 100% true to form. But since I can only guess at it, I would say that this converges to this as sample number goes to infinity, right? So I've also written this way. I say as n goes to infinity, right? F hat goes to F. So anything that is less than infinity is going to be what? It's going to cause a disparity between those two. So the disparity is a balancing game. The balancing game is my subset is not the perfect representation. Matter of fact, it's only a fractional representation of the true underlying system. Thus, I would say that the closer I get to understanding that specific sampling group, yeah, I'm good. I do a good job at understanding my training data, but what am I actually doing? I'm skipping out on understanding the true f of x. I've missed the objective function. I'm now modeling some subset version of f of x. That subset version is, specifically in this case, the training subset. So understanding the disparity between how those sets perform allows us to be able to understand a little bit more about why we can't get a perfect version of training and then apply it universally to testing. Because just like the training only contains some of the variance, some of the characteristics of the underlying model, testing also contains only some characteristics of the underlying model, and thus there's flaws in both. However, if I get something that applies relatively equal to both, what am I making the statement of? I'm making the statement that the standard deviation for training, right, and standard deviation for testing are essentially the unique characteristics of the offset. Each of these deltas from their true underlying system are not as impactful on the model. So you remember previously when we talked about the idea of we had a target, right?
Yeah.
And we said that we had points that were right here in the middle, this being high accuracy, but whenever they offset and they were out here to the side, we said that was biased. It's biased because I have to adjust my target. I have to translate it up to the center of the system. I have to translate it because the mean of that distribution has changed structurally. So since the means of the training and the means of the testing are in slightly different spaces, guess what I have to do? I have to allow some error to occur in training in order to be able to allow that equivalent amount of accuracy to transfer over to testing. So meaning I have to, if training is up here and testing is over here, right? I basically need the vector that translates me somewhere in between the two. That happens here. That happens here. It happens where the trade-off of I can't get any better at training without sacrificing testing performance. Because of the fact that the variance generation with respect to model, training to testing, is variable in that sense. Right? So I can't have consistent performance, perfect consistent performance, both against both. At least that doesn't seem likely. Yeah.
So does that mean you're like inputting some noise? So you're just expanding that target out so you can get in between the testing and the training to get relatively both?
Occasionally we will insert noise into data.
Okay.
We don't on a regular basis in what would be considered traditional models, like regression. At least not with what would be considered deterministic modeling, like we do with neighborhood approximations, right? So our neighborhood approximation regression, our mean square error assessment, is based upon an iterative development, right? We keep iteratively improving the process. So let's look real quick. I have a little web link here of I think I posted it already, but what did I do with that? Yeah, there it is. Okay, I'm gonna take a look at this real quick. We didn't look at this one last time, did we? Okay, I have two classes, and sometimes it messes with my head terrible. I don't know where we start and stop. But they kind of almost caught up to you because we didn't have Monday. Okay, so now we're hopefully on parity and I'll be in the same places with you most of the time. Given what we know about the regression model, we have a series of points distributed over a region, and we want to try to understand how they're related to one another. Okay, so our mapping mechanism is going to employ during the training a process that attempts to do what? Spread the blame around, right? Something's wrong here. I gotta make sure, that we evenly distribute the error, okay? Because if I don't, then one person's gonna be perfect and the other one's gonna be way off. Okay, so spread the blame around. That hopefully will quantitatively ease our global process. Now, what I end up with here is in the training, all of the error comes from irreducible characteristics. Because at this level of complexity, I have captured some of the variance, right? I've captured some of that slope as the space designs, but I am not able to perfectly encapsulate all of the variance in that system. Now I can prove this by going through and sampling again with some testing data. Now this testing data, sourced from the same occurrence, right? The same underlying generative function created it. But as we note here, some of the samples can have more noise, right? Or they can be offset more from what we would see as the localized mean of the data than what we've experienced within the training set. So this becomes a little problematic. Just the selection characteristics, the randomized sourcing of the samples can create large disparity between training and testing sampling. But at the same time, we could say that it is still indicative of the likelihood of a sample to fall within whatever range of values are going to occur. So that makes it a simulation of what it would be like had we gone out and collected this many more samples from the underlying distribution. So my goal here is going to be, in this particular case, trying to find a parity between training and testing performance. So my first step is going to be to implement a complex model, right? So I want to go in and add the system to have a significant degree of capacity to understand the little jitters and jaunts. Now notice, it's not fitting to any of the testing data. It's just fitting to the training data. It's perfectly fit to the training data. So what happens with respect, just see if you predict this in your head, what's going to happen here. Okay? All of the error now is happening with testing. There's this little sliver up here, right? You know, like 0.1 something, tiny values we can't, totally encompass by the 25th degree of freedom, whatever model we put up there for those 12 samples. Okay, massive overfitting comes from an attempt to try to drive down the error, total error in the system, and sacrificing the ability to apply to a new or generalize to a new data set. This is where I say the data set dependence characteristic comes in strongly. But what I would look at here is that all error decomposition can be broken down into the square bias characteristics, some aspects of the variance, which is set to set characteristics, and then noising characteristics, which are not addressable. Notice here we have the same formula mathematically that we have in our system. They just use the term noise rather than eta, the irreducible characteristics. So if I want to look at how bias affects the system, bias is represented as the square of the delta between f hat and f of x, right? So if I say that biasing term is minimized when I minimize MSE, mean squared error, then that seems like a good thing, right? Once again, sociology says bias is bad. We say bias is what? Just the inverse of error. So I'm thinking about this from a perspective of error. This is my target. This is my guess. The delta between these, the total magnitude of delta between these is seen as the same thing as that square biasing term. So if I attempt to model characteristics of variance by going through and adjusting the Fourier parameter capability of the underlying model system, what do I have up there? What are all those little lines? What are the yellow ones up top? What are those? I've been talking about them a lot. They're models, right? That's what I mean by model. I'm saying I'm making a guess at how the data is interrelated with itself. So I have many candidate models that are available in this plot. The candidate models are expressed in terms of the bias variance characteristic on this bottom plot. This is a real bias variance plot, essentially one that's generated from the data that's given up above. Not the idealized version that we looked at that had perfect sloping lines. So whenever I look at the system, I notice that the biasing characteristic sort of bottoms out, and the variance characteristic bottoms out as well. And I actually have a period through the middle of this system in which they're essentially equivalent to one another. They don't have that hard crossover that we saw previously. So where do I select my model from? How do I select the model in this case? This is largely attributed based upon the training data.
The green one?
The green one?
Yeah. Because it's
characteristic?
because the
So
wind.
where would I select for the variance characteristic? This is a double optimization scenario. What two things am I looking to optimize?
Intersection.
Let's go here a minute, okay? I'm gonna keep going, we're gonna keep talking about using this plot. Okay, in this particular case, I have fitted down to a subset of the models I had previously, right? I've selected for those that fall far outside the range of interest. They either have massive bias or massive variance. Now by zooming in on the subset of this region, what can I see here? Where might I pick for this spacing?
Mm,
Does it need to be zoomed in more? I can only zoom in a little bit. What about that? Model complexity range, does that look about right? I think the error is too high, personally. I'm not sure why they selected this particular subpoint. But their claim is that the variance is minimized relative to the min bias, okay? So they looked at trying to minimize the noising characteristics relative to the bias. Down there at the bottom, we have bias. What's bias? That's the testing set maximized to error, essentially, right?
yes.
When we are becoming set dependent, we minimize bias. We notice that as bias is minimized, we're going to increase the variance. So
Yes.
when I say that I'm selecting at minimum bias, but I'm also looking at trying to minimize error. Think about this as a multi-factor minimization attempt. I want to try to minimize error globally. How do I minimize error globally? Because it is the summation of these three elements, the minimization will actually require a balance between those characteristics. So let's scroll down a little bit further on. I can reproject this utilizing just the region of complexity I'm interested in, and I get something close to my previous underlying plot as I expand out the data points for the subsamples that I've been given. Now I want to go down and look a little bit about something we talked about previously. I'm going to randomize the training data, and I'm going to crank back the smoothness of this system. What do we notice there about the points between the approximations?
So training has.
Essentially, they're just linear segments from point to point.
Yeah.
I've decomposed this into a series of individual linear models, and utilizing that neighborhood approximation is essentially saying I'm using a neighborhood distance of 1, whatever my closest neighbor is. I use that as my local regression baseline. Now notice there what happens. At smooth as 1, or smooth as 0.1, right? What do I have? I have 0 training error and maximized testing error. As I increase the smoothness of the system, that means I increase the width of my training region. More of my samples are going to try to take into consideration the future likelihood of the sample data. Notice as I crank this up, what happens to the training error? Training error is going up, but notice something else about the testing error. It's coming down, right? So notice there was a point at which I'd reached a minimum with regard to the testing error, right? Without increasing it again. Notice it starts to increase again whenever I go up above that value. So while I'm at minimum training error and minimum testing error, I have created what? Minimum variance between the two. The delta between the error between the two sets is minimized. I would then say that the resulting error, the remainder of that error of the system is what? Generative to what?
Bias.
It's generative to irreducible components, right?
Yeah.
At least the most part of them seem irreducible in that sense. Now we have some other data. Variance with respect to the system is delta between the two, okay? It is training performance minus testing performance. That's going to give us our variance between the set. Minimizing training error is potentially going to maximize testing error, or at least with respect to what we talked about beforehand. So no matter how I go about this system, there's always going to be a point in which I would minimize the testing error. Now notice something interesting here. This is very uncommon that this is even possible, but it does occur. Notice something weird here. What happens to testing error?
It's less than the training.
It's less than the training error. Why would that happen? How would that happen? It's just a quirk of the distributions of the sampling. Which samples got put together, it is actually indicative that the training has slightly more shift or maybe skewness in its selection bias of how the individual samples were sourced out in such a way that it creates kind of a weird distribution that if you smooth this out enough, it'll match really well to the testing data, which could also be a selection bias characteristic that isn't necessarily indicative of future performance. Now, generally what we say is we're actually going to be underestimating the potential future performance of this model. It may actually perform better than even this testing arrangement. But notice here, this is kind of a curve inversion, but at the same time, I have a minimization while I have sub-maximization. So essentially a smoothness of 0.65 here is likely to actually be our best fit point. While bias is actually not minimized, variance is at a min, and I have good quality of performance in both cases. But the overall error is still relatively high. This might indicate this actually is not sufficient in terms of flexibility to adequately capture the data that's going on. This might actually be indicative of an underfitting. Typically, if you have an inversion of that curve, it's more indicative of an underfit than an overfit. Okay. This also has on here an understanding of nearest neighborhood approximation, right? So we can go and we can look and see how the little, we'll make it a little bigger and randomize some data. We'll see the little spider crawling along the line and how it determines which group it's a member of based upon its closest associated values. This is very similar to how we utilize a regression framework to tell us the ideal value based upon the neighborhood that it's surrounded with, right? So determining the scale K of the number of nearest neighbors associated with the value will give us that understanding of the space that is defining the regression line or the characteristic here. But this one is special in the effect that this is what we call the discriminant boundary. Let's go look at something real quick here. We talked already about, I'm sorry. No, that's fine. That's the wrong slides. What am I doing? Okay, we talked already about bias variance trade-off. We've cleared that up again. I expanded on our understanding and tried to make it clear. This shows some examples that are related to the 3 examples that we looked at previously and what the real data bias variance looks like. I don't know if we looked at the slide last time or not, but this is what I say, like more real data. As bias decreases, we have a subtle increase in variance up to almost this like asymptotic relationship to variance. This is just a massive divergence as the error starts to push away, indicating that I've overfit to the sample. In this case, I have this weird consideration for a low dimensionality model, and I look at what happens whenever I attempt to take something that's linear or maybe cubic and attempt to try to fit it in high dimensionality. I'll end up overfitting very quickly, right? So I increase the variance very, very quickly, and the bias completely flatlines, right? We go down to a minima, and do we just stay there? So when we go down to a minima and bias, but then we continue to increase variance, that's all loss, okay? We use the term loss to describe that disparity in the quality of the model. Loss is the metric that we look for in all models, and we establish it as a value that we're concerning ourselves with. We say, what are we losing by increasing the flexibility or changing the parameterization? Likewise, over there to the right, we have a system that is fairly high complexity, high dimensionality underlying. And while the MSE is minimizing and bias is reducing overall, variance does sort of rocket up down there toward the end as we increase past a reasonable degree of flexibility in order to model the underlying distribution. Now, I was talking previously about this idea of the the nearest neighbor plot that I showed being a classification. Now, when I recognize that we haven't really talked about the idea of classification, but I will tell you, you already do it constantly. When I talk about classification, anybody want to take a guess at what I'm talking about?
0, 1.
Okay, that's binary classification. That's a good version. But what does that actually mean? Is it puts things into what?
Classes.
Classes, what's another word for class? Category, okay? All right, so class, category, group, all of those things are the target characteristic that I'm interested in. Now, what I'm asking you is to imagine with me a system that takes, let's start off here with spam and ham, right? We're talking about good versus bad emails, which ones we're interested in. And I say that the better off I do at this separation, the system will place good emails in your inbox and bad emails in spam folder. Now, if I start putting them in the wrong places, that's a misclassification. Typically what I end up with is a situation where I tend to err on the side of caution. If I think that it could be a bad email, it goes to the spam folder, right? Because that might be the better process. That's a stricter model. But what I'm actually doing is, it's just like in the grocery store where they have like the little stickers that they stick on top of the bananas, right? Mm-hmm. So, hold on, gotta go back to my map. All right, so I have to go back to the appropriate section. I have some input data, right? I've taken the little banana stickers or the little apple stickers, Chiquita, Dole, whatever else, and I got the little roll of them off, and I'm sticking them on the fruit as it comes off the line, so I know what's what. Right, I'm a machine, I don't understand the difference between fruit. I can only distinguish fruit based upon characteristics of the fruit. So what we say is that when I place a category on it, I'm clustering them together, I'm grouping them together, and I'm informing you with a supervised model with a label. So previously we've used the term target, right? But we could also use the term label. Label is a type of target. So label can be in the position Y. So what we said previously is that I stick a sticker on it, and whenever I'm running this system, I'm going to put the groups apples, peaches, bananas, and I'm going to establish the process by supervised learning. I say, this is an apple, right? It's like watching children's television shows, right? You go to the model, you go, this is an apple, this is a banana, this is a peach, it's orange, right? So, and the model eventually goes, I get it, and then it gets a generalized concept to it, and then you go, what's this, right? And it goes, it's a banana, and you go, no, it's a peach. That's what we're doing, right? We're incentivizing the model to get the right answer by encouraging it to make the right decision, okay? I'm not encouraging any kind of abuse or anything. Don't be abusive to your models, that's awful. But we would then later on assess the model's performance based upon inputting some data that was not yet labeled, right? Running it through the model system, and what ends up happening. It puts bananas, or puts the peach stickers, puts banana stickers, puts the apple stickers, and then we end up with sorted lists indicating the elements of the target space. Okay? What happens if the apple goes in the banana category? We consider that a whole error. Okay? Previously, whenever we have quantitative error, we think about how far away we are from the line. With quality-based error, we end up in a situation where the errors are whole, right? It's a full binary error. You either got it wrong or you got it right. There isn't an adjacency metric that we utilize for that system. Now, what we might be able to utilize is we might be able to utilize some spatial characteristics, and this is where we talk about the idea of a discriminant. That's where if you're below this line, you're an apple. If you're above this line, you're a banana. Okay? That's the target we're talking about or thinking about, is creating lines that divide things based upon the characteristics they're made up of. Now structurally, we are going to utilize these systems for imaging, personal computing, in terms of like, what do we use image analysis for now? Image search, automatic annotation. All those tools are available for us from Google, utilizing this technology. So when I think about the idea of classifying things, I might think of a qualitative categorical approach to one of the things we talked about in one of our early lectures, which was the idea of the ability to take sample data, right, handwritten digits, and convert them to their numerical categories. So I see a picture of a shape, and I actually can convert a picture of a shape into the appropriate numerical designation at that position. With that characteristic in play, we build our classifiers to be able to learn and label based upon previously known information, and then extrapolate out to new, unknown information. So in this situation, the training versus testing paradigm implies the notion of learning from labeled data, and then attempting to label unlabeled data. All right, what we've done is we've stripped all the stickers off all the fruit in the testing. And then I'm going to hold it up and I'm going to ask you which one it is. Then I'm going to keep my own private tally off to the side here to see whether or not you learned from the categories you had to be able to predict the appropriate categories for the unlabeled samples. Then it would imply that I could do what? I could set this loose in the real world, hooked up to a camera, to do something that essentially augments the capacity of some human user or something in natural space. Our goal with these systems is not to replace people, never to replace people. I don't advocate for that at all. I think it's a terrible idea. I think we should figure out ways to build models that improve our capabilities and work alongside us in general. And that is a supported perspective by a lot of the emerging ideals and processes we're working with. So categorization systems like this need to be developed with, or any system model needs to be developed with the notion of improving and expanding the capacity of the user, helping us not miss things as we're developed and incorporation. Yeah.
So you said we don't want to replace with machines, right? But
Correct.
it is possible. Like, can it be replaced? A human can be replaced by a machine. Like,
I think the question is, what are you attempting to replace?
okay.
Right? Are you attempting to replace someone for the purpose of attempting to reduce your costs so that you can have greater profitability? What's the ethics involved in that? Removing individuals from being in their ability to control the means of production? Right? So the only goal, the only objective I can think about when you think about replacement of an individual with an automated system that would actually be even slightly ethical is the idea that we create a new job that's more interactive, more exciting, more enjoyable than the previous mundane, boring, repetitive job that we had people doing in that autonomous space. Okay, so when I think about it from that perspective, classification tools are the ones that probably do the closest thing to our human capacity with regard to the jobs that we send people out to do. So most things can be decomposed into classification or regression tasks. So with these two tools in place, you can usually replicate most human capacity type behavior, at least to a reasonable degree. But do we want to turn over there's certain things we don't want to turn over robots. We'll continue to talk about those. So thank you for your patience. I will see you guys on Wednesday.